Good afternoon, ladies and gentlemen, and welcome to our webinar, Understanding the Cooling Requirements for a High-Performance Electric Traction Motor. We're going to be discussing the 2010 Prius motor, and specifically we're going to assess that motor with a commercial software product called MotorSolve. MotorSolve simulates a full experimental process for physical prototypes. In essence, it's virtually prototyping. MotorSolve provides for multi-physics coupling, and it allows for a full-time transient solution. MotorSolve is based on electromagnetic simulation, and in particular 2D finite element method technology. Throughout the product, solutions will be based upon either static magnetic finite element method or transient magnetic finite element method. And in particular, the considerations that we have for electromagnetism include temperature-dependent nonlinear materials, motion-induced effects, and material losses associated with either eddy current or hysteresis effects. The thermal simulation part of MotorSolve is based on 3D finite element method technology. Throughout the product, solutions can be based on either static thermal finite element methods or transient thermal finite element methods. In all cases, the thermal considerations include conduction, convection, both natural and forced, and radiation, both internal and external. As we assess motors, one of the key failure considerations is with regard to insulation. And as you can see in this IEEE graph, the lifetime of insulation can be depicted by a series of curves, depending on class, and the lifetime associated with temperature. And as we design motors, we need to make sure that we understand what the peak temperature might do to the overall lifetime of the machine. Another thermal consideration is what the temperature might do to the permanent magnets of the machine. And this is a representative curve from vacuum schmelz for one of their neodymium iron boron magnets. And the family of curves represented here are a function of temperature. And it's very important to note that we need to know where the magnet resides temperature-wise so that we understand whether there's a possibility of demagnetization as a result of pushing the magnet beyond the knee in the second quadrant. MotorSolve is a design software. It has specific interfaces which allow you to assemble the components. You define each component, you assign them materials, and then you define the excitation and the initial conditions for any given experiment. Once the experiment is set up, you run it, and then you review the machine's performance. As I mentioned, we're going to explore the 2010 Toyota Prius motor. This is a cross-sectional view of the machine. The Prius is a brushless permanent magnet motor. It's comprised of a 48-slot M19 lamination. It's comprised of an 8-pole interior permanent magnet rotor with M19 rotor core material and neodymium iron boron magnets. As we go through the webinar this afternoon, it's important to note that, courtesy of the Oak Ridge National Laboratory, the laboratory results which are shown and reported are courtesy of a report that they provided in March 2011 entitled The Evaluation of the 2010 Toyota Prius Hybrid Synergy Drive System. This is the MotorSolve interface. In fact, this is the default brushless permanent magnet motor interface. And the interface is split into 3 areas. I'm not going to dwell on the interface for very long, but I thought would be instructive to share it with you. Should you have a desire to look at more detail in the interface, we have additional webinars that we've posted previously, which will give you a much more in-depth assessment and portrayal of the capabilities. Anyways, you can see here that in the tree on the top left here, you have control of your design. And in fact, you can have more than one design in the same model. And they can be duplicates of one another with small changes, or they can be completely different. It's up to you. But as we assess the nature of a particular design, you can see here that we've got a series of things identified which make up the machine. And first and foremost, we have the general settings. And you can see here that we have basic nameplate kinds of features that are required for things like supply voltage and rated current and rated speed. And then we also require some notion of the overall physical envelope of the machine with respect to the outer diameter and the stack length. And then we have separate areas here for defining how you would describe the rotor and then the stator. One other key point here also is that you have inputs for energy balance associated with your machine, so you can enter friction losses, windage losses, and any stray loss that may be resulting from your machine. As you click on other members of the tree here, you have additional parameters that are available to you for describing your machine. And these would include the magnet thickness. For instance, you can change the magnet thickness very quickly and describe the machine as you need. Additionally, with the stator, when we go into the stator, we have a geometry-based area, which again allows you to change the nature of the machine based on what you're actually trying to model. And after you've finished the geometry side of the stator, we have an area for describing the winding. We have conditions for the drive. We have representations for the cross section. Here we have an over-under. We can also do a side-by-side. You have the ability to describe the wire in the winding, either with a fill factor or with any number of standard gauge wire. You can do rectangular wire, or you can simply enter diameter or area. And then you have full control of the layout of the winding. And you note here that we have an automatic layout capability, which allows you to pick from the possible and available balance winding configurations. And so these are automatically done for you. Just as a matter of reference, simple toggle of the pull down gives you a quick representation of things. If you don't desire to use one of our automatic layouts, you can switch this to manual and then enter your winding layout manually in this area here. Additionally, we have a construct area for describing the end winding of the motor, and this is very important for overall impedance character of the winding. Note that back in this interface area we have a full representation of the winding, both from a resistance and an inductance perspective. Once you finish with the geometry part of the machine, you would go in here into the material area, and with a simple set of pull down references you would go and access the available libraries, which are extensive. for any range of materials, and you simply locate the material that you're interested in through this scroll bar, and then activate the choice that you have for the material. You have options here that are representing how you might introduce the stacking factor. We also have factors that allow you to control and adjust for any sort of iron loss adjustment based on the material performance. And one last item to note, there are some machines where the shaft and or the hub have impact on the magnetics, and you can toggle this pull down to yes if that is indeed part of the configuration and concern that you might have for your material or for your motor. From the thermal side of things, since we're going to be doing a coupled solution here with the Prius, we're going to talk about this just briefly. The initial thermal setting is your ambient temperature. By default we've set this to 20, but you can set this to whatever you desire, which would be consistent with your laboratory experiment. And then further, we've got a series of additional parameters which allow you to describe, for instance, the housing thickness and the end winding region. And note here that anytime that you're in one of the associated parameters, there's an associated label over in the drawing. There's also a more verbose description of the parameter below here in the toolbar area. But you have full control of setting up and describing the machine along the shaft. Then we have an interface area which allows you to describe constructs that we're calling interface gap. And anytime that you have two surfaces that meet, there's an equivalent thermal surface associated with that gap, and we allow you to enter an associated thickness for that gap, and this is very dependent upon manufacturing processes, and that's why we have factors that you can adjust. But then we go into the cooling configuration area. Our default is totally enclosed, non-ventilated. You can toggle that to totally enclosed, fan cooled if you'd like. Or additionally, you can toggle and add spray cooling. Now I mentioned to you that there's also thermal radiation effects. And there's a notion here of the full control or the full representation of radiative physics known as emissivity. And the default here is a factor of 0.85, and you can adjust these. There are certain things that change at possible emissivity. Some of these things could be surface roughness or smoothness. It also could be the color of the paint and or the sheen or glossiness of the paint. And then additionally we have convection coefficient adjustment factors here, which allow you to adjust based on the cooling, the precise cooling of your machine. This allows you to correlate with any manufacturing processes or forced convection cooling that you might have, which we don't have 100% implemented into the product at any juncture. And then of course, because we're interested in doing a thorough assessment, we have a thermal materials area, and you simply go into this thermal material area, and again you'll pull down and toggle on to appropriate material for the component in question. Now note about materials here, you can enter any material that you need or want or have implemented in your real devices, and it's a simple matter of adding to the library. And it's very important to have an idea of From an electromagnetic perspective, the permeability character, the B versus H, if you will. From a thermal perspective, we need to know the thermal conductivity, we need to know the specific heat, and we need to know the mass density for any solids. For any fluids, we need to know those same things, plus we need to know the viscosity characteristic of the fluid. Now that's the setup of the overall machine. Now, the product wouldn't be complete without some actual experiments. So you can see here that we have a set of predefined experiments that you can run. They range from cogging torque to back EMF. Additionally, you can do a full motion analysis. One of the very key points and characters of the MotorSolve product is that you can actually see the electromagnetic and thermal fields in the machine, and this allows you to dive in and see parts of the machine that you can't see with your eye. So there's a much broader ability to assess the performance of the machine than you can actually do in the lab, because you can go down onto the micro level. And at this point, let's go and we'll look at the base configuration for the 2010 Prius. So here we have the MotorSolve interface with the base model loaded for the Prius. I won't go over too much of the geometry details here, aside from to say that due to the innovative notion or constructs that folks can explore, we have implemented the ability to import both the rotor and the stator separately. You can see here that we've got a very complicated rotor structure with hollow core and spokes for the interior of the rotor. We've got very unique features centered around the magnets, as well as a dimple in the outer perimeter of the core. And this allows us to very nicely adapt the interface to your needs, and allows you to innovate as you need to without being constrained by a particular interface choice or setup with respect to that sort of thing. The material for the Prius, as I said, is M19 and neodymium iron boron. You can see, for instance, that we have a lap winding. We've got a series of number 20 gauge wire with strands in hand, total of 11 turns associated with the winding. That's pretty much the basics for the setup of the machine. We're going to do back EMF test real quickly here. You can see here that we have about 323 or 324 volts peak. If you take the square root of 2 and divide that by that, you get around 225 volts RMS for 6,000 RPM. That's consistent with the Oak Ridge National Lab data. If I toggle this to 4,000 and go back to my back EMF, you can see here down that's about 215, 216. That's consistent with 150 volts RMS. And then I go down to 2,000 as another testing example. You can see here that we're about 108 volts peak, which is 75 volts RMS. Very nice back EMF constant. It's very linear through the 0 to 6,000 RPM, and gives you comfort that you've modeled the machine according to the principles that were desired. Now, as a precursor, we're going to actually just do a simple flux plot from 0 to 2 Tesla. And in just a moment, you'll have a shaded plot throughout the space of the machine representing the flux density. Note that you can see areas where the flux density has exceeded 2 Tesla. And so the Prius is very high flux density, and the design is pushing technologies and materials at this point. Prior to moving on to the thermal side of things, I just want to remark here that you have the option for a whole range of controls associated with your experiments. And we just did a flux density test, but we've got with 100% of rated current here, if we were to change this to 0 and recompute and get another plot, we also can change either the rotor position or the advance angle on the drive to show the implications of that, and that's particularly of interest for IPM motors such as the Prius. But let's move on now and look at our first thermal-based solution for the Prius. In total, we're going to explore 3 different thermal models of the Prius machine. The first of these is going to be the exact test condition specified by the Oak Ridge National Lab for the 25 kilowatt operation at 3000 RPM. Prior to showing the actual test, we're going to go in and look at the initial conditions which are required. Initial conditions are that the ambient temperature is 35 degrees. The machine is a totally enclosed non-ventilated machine. However, it has spray cooling. And you can see here that we have a 25 degree coolant temperature. We have roughly 75 millimeter per second velocity on the jets. And so now let's go and look at the prescribed experiment. The experiment is a temperature experiment. The temperature experiment has a duration where the machine has no excitation for roughly 160 seconds, and then it has about 2,000 seconds of excitation, and then roughly 90 seconds where there is no excitation. And here is the resultant temperature for the winding. And you can see here that using our handy vertical line, we can track the temperature at any point in time, cross-reference things. Perhaps a little easier though is to look at comparison. And here you can see I've plotted the measured values for the winding by the Oak Ridge National Lab in green, and in red the MotorSolve simulation. And you can see that the values track very nicely throughout the entire solution region. And now if you look, we've chosen to do this on just the coil as an alternative. We'll do this for the magnet. You can see here that the magnet has a slightly different profile. It's a little bit slower to react to the heat imposed from the excitation. And the overall temperature for the magnet peaks out at around 112 or so, 112 degrees C. And now instead, if we look at a flux density plot, we're going to do 2 plots sequentially from 0 to 2 Tesla. The first one's going to be at our ambient, which was 35 degrees, and the second is going to be at the end of the transient time period. So let's go ahead and initiate that experiment. Here you can see the flux density shade plot, and this is at ambient temperature, so 35 degrees. And now if I toggle on this parameter here and tell it that I want to look at the operating temperature after the transient response, it'll take another moment, but we'll have that shade plot. Okay, so now we have a finished plot at the end of the transient cycle. I'm going to zoom into the magnet area here and review the flux density. in these permanent magnets. And we can see here that we have roughly a Tesla, or 1.1 Tesla. If I switch back to the previous, you can see that I have about 1.2, and we've lost roughly 10% of the permanent magnet strength, which is consistent with the loss, magnetization loss parameter for neodymium. And now we'll run one more experiment here. We're going to look at the time averaged solution. Initially, this would be your ambient temperature solution. So we have just under 80 Newton meters of torque. We've got 92.8% efficiency, and we have 1.95 kilowatts of losses, made up primarily from the winding, but you can see the distribution of the losses in the other components, as well as some that do exist actually in the magnets themselves. If I toggle this to my performance criteria following the transient cycle, so in other words after the 2400 second performance, my torque is dropped from the initial value down to 73.9 or 74 Newton meters. So we've lost a little bit, maybe 5% of the overall torque. Our efficiency has dropped roughly 2% from the previous. Our losses are significantly higher, with 2.5 kilowatts, again primarily in the winding. But you can see the overall performance of the machine as a function of either the initial ambient temperature values or the full temperature equivalent. Okay, so now let's have a look at the thermal fields. Initially, let's look at time t equals 0. So here we see a shade plot of the cross-section of the entire motor, although it's broken into symmetry and we have just wedges here. But you see the cross-section at time t equals 0. So now if we go 500 seconds into the solution, you can see that the winding has started to heat up, and you have a distribution of hotter temperatures in the end winding. If we go to 1000, you can see further 1500 seconds. Go to 2000, and then go to the end. You can see the full distribution of temperature in the machine. One other thing to note here, with the mouse rollover, you can see the local temperature. And if I go into the magnet region, you can see that I've got roughly 104, 105 in this magnet here. Winding is at roughly 116 at this point. Before we move on to the next experiment, I just wanted to underscore temperature that we discovered. This temperature profile. For the coil, we had a peak of 134 degrees. The magnet peaked at 112. The second thermal model that we're going to explore has the same geometry, has the same initial conditions, except it has a fluid jet velocity of roughly half, 37.25 millimeters per second for the velocity. We're going to review the same experiments. So the first one we'll do is the temperature run. Note here that at the peak temperature we have 168 degrees, so it's a full 34 degrees above the full spray. If instead we look at the magnet now is at 144 degrees, which is 32 degrees above the other experiment with full spray. The ambient temperature time average performance is the same. So if we look at the steady state, performance. We have a little bit over 71 Newton meters for torque. Our efficiency has gone down to 89%. Our total losses are 2.7 kilowatts. 2.3 of those are from the winding. Now if we look at the instantaneous fields for the magnetism, here we see a shade plot of the flux density. Again, this is at the operating temperature after the completion of the duty cycle excitation. If I zoom into the magnet area again, I have reduced flux. It's not much below the previous, but it is 4 to 5 degrees below on average. If I look at the thermal fields, we'll start with a time instance of 0. Here's our thermal shade plot, and we're going to retrace our steps from the previous model and step through 500-second intervals. Here you can see the response at 500 seconds. Here's the response at 1000 seconds, 1500 seconds, 2000 seconds, and 2300 seconds. That I've kept the legend ranges the same so that we could see what level the motor is hotter than the previous machine. Basically the entire stator and most of the rotor are above the temperature, the maximum temperatures of the previous model. If I rescale this, you can see the distribution of the temperature a little bit better. But you can see that you have magnet temperatures mid 130s. The end winding is in the high 140s, almost 150. The final machine that we're going to review today is the same Prius motor, only this motor configuration is such that there's going to be no cooling. See here that I've turned the spray cooling off. So first let's look at the temperature response of the winding. And because of the nature of the drive and the current required to generate the torque, without cooling, this winding will reach a temperature of 279 or 280 degrees C. Likewise, if we look at the magnet reaches 216 degrees C. If we look at the template data, the torque is reduced all the way down to 62 Newton meters. The output power is substantially lower than any of the previous designs, as would be expected. It's only 19.5 kilowatts. Our efficiency is dropped to 85.4%, and the winding losses are up to almost 3 kilowatts. Most of the other losses have remained constant during the various experiments, but note also that the magnet losses have increased by a factor of 2 from ambient with the increased temperature. If we look at a shade plot of the flux throughout the machine, we end up with this distribution. If we zoom into the region of interest, at ambient we're still with 1.2 Tesla throughout the magnets. If we go to steady state operating area, we see here that the magnets are now below a Tesla, so we've lost more than 20% in the magnets. So let's have a look at the thermal field plots for this machine. And the first one we're going to look at is with a range of temperature similar to the previous two. Note that the entire motor is above 128 degrees C at the end of the time sequence. So let's rescale with our upper bound so that as we move through the time sequence we can see the distribution of temperature change. Here we have the temperature at 0 seconds. If we Modify that to 500 seconds. We see the winding is already at 199 degrees, 100 degrees essentially at 500 seconds. If we move to 1,000 seconds, we're now up in the 150 degree range. 1,500 seconds. We're up around 200 degrees. 2,000 seconds. We're now up above 250 degrees C in the winding and mid 180s for the magnet and rotor area. At the final time step, the magnets are at 213 or 214 degrees. The winding is at 260 plus. Clearly these temperatures are not going to be sufficient for a long-lasting machine. So now we've gone through all three machines, and let's look at a summary. Here we've plotted the temperature response of the winding for all three experiments. You see here the full spray response, the half spray, and the nose spray. And the Prius is a very interesting motor for many reasons, one of which is that they have automatic shutoffs for the power or the drive associated with the winding when the winding temperature gets too high, and that can be preset or set differently depending on performance and things. But the Oak Ridge National Lab chose to stop this test so that the winding would not get higher than 135 degrees. So if we look at that being the case, the full spray motor condition can go all the way out to roughly 40 minutes, just under 40 minutes of operation at 25 kilowatts of power output. If we now look at the half spray case, and we want to maintain a temperature of less than 135 degrees, it occurs at 1,062 seconds, which is roughly 17 minutes. And this is a dramatic decrease from the full spray of a little more than half. If we then look at our no spray case, the motor could function with outputting 25 kilowatts for a little over 700 seconds, so roughly 12 minutes or so. This gives you a very good feel for the necessity for cooling and the overall performance hit that you would take as a function of the different kinds of cooling that you might choose. As a further summary of the assessment that we've made with our machines today, I've tabulated the results for the different experiments, and you can see here the transition or the trend of the torque, where we started at 80 Newton meters ambient, reality in full spray after operation for 2,400 seconds was 74 Newton meters. The half spray is 71, and with no spray it's all the way down to 62 Newton meters. The efficiency, which started up almost at 93%, drops to 90% with the full spray, and the operation after the full transient, 89% efficiency for the half spray, and then the no spray is only 85% Additionally, I've tabulated here our winding temperature. Note that we started at 35 degrees. The full spray was 134. The half spray was 168. The no spray was 279 or 280. The magnet temperature was 112 for the full spray, 134 for the half spray, and 216 for the no spray. This concludes our webinar on understanding the cooling requirements for a high-performance electric traction motor. We thank you for your time, and at this time we'll open it up for question and answers. Thank you, and have a good day.